Hi everyone, my name's John. I'm here with my colleague Vivek, and we're going to talk today about a new general approach to source separation. Source separation problems appear in a variety of problem domains, separating the voices of multiple speakers or multiple instruments from an audio recording, separating reflections from an image, or separating brain signals from an EEG. Source separation also has been applied to telecommunication technologies like CDMA that may have direct business interests for Qualcomm. Before we dive into our approach, let's take a brief look at the state of the art in source separation. For many source separation problems, the best current algorithms are deep regression models, which are trained on input-output pairs of mixtures and components. These models are fed a mixture as input and predict a set of components as output. You can train these models given a data set of components by randomly selecting components, mixing them together, and asking your model to predict the original components given the mixture. While this regression-based approach is very popular and successful, we observe that the outputs of these methods usually contain perceptible artifacts. They don't quite look or sound like components from the original dataset. There is good ongoing work to improve these regression models, but we propose to solve the artifacts problem by taking a very different approach. We're motivated by the observation that, in contrast to source separation models, modern generative models are largely free of artifacts. On the left are samples from two generative models. The first is trained to produce images, trained on pictures of celebrities using the GLOW model. The second is trained to produce audio, trained on musical recordings using a WaveNet model. Let's listen to the audio. Generative models continue to improve, and one goal of our proposal is to find a way to use the latest advances in generative modeling to improve source separation results. The last audio sample you heard was from a 4-year-old model. Here's a sample from a model released 2 weeks ago by OpenAI.
I want to see your face again, like your sunlight by this morning.
As you can see and hear, these models are quite good at mimicking the data generating distribution. Our approach to source separation will use a generative model as an explicit prior about what the components of a mixture are supposed to look like. Let's flesh this idea out. Given a mixture M of unknown components X, we can perform source separation by sampling from the posterior distribution over the components given the mixture. The posterior can be written in terms of a likelihood, P of M given X, and a prior, P of X. The likelihood term forces the components to sum to the given mixture, but doesn't constrain what the components look like. The prior forces the components to look realistic, but doesn't generate samples that add to the given mixture. Samples from the posterior reconstruct the mixture well and are likely under the prior. A generative model trained on mixture components is a powerful prior for source separation. This perspective lets us directly apply cutting-edge generative models as priors. Furthermore, we can easily adapt our algorithm to different problem domains, so long as a good generative model has been published for that domain. In contrast, the regression approach requires us to train regression models specifically for each separation task. The primary technical obstacle to our approach is, how do we sample from the posterior distribution? Naive gradient ascent on the posterior likelihood fails catastrophically. The problem is that the likelihood surface is highly non-smooth and non-convex. Here's a cartoon image of what the prior likelihood looks like. In most regions, the data is highly unlikely, and the loss surface is flat, resulting in vanishing gradients. As a result, optimizing the posterior initially makes some progress on the mixture constraint, but makes very little progress on improving the prior likelihood. We derive an answer to the sampling problem using techniques from a recent breakthrough paper by Yang Song and Stefano Erman. Their work demonstrated an efficient way to sample from a generative model using annealed Langevin dynamics. We can adapt their algorithm to sample from our posterior distribution. The idea is twofold. First, we smooth out the distribution by convolving it with a high bandwidth Gaussian. This smooth distribution is easy to optimize, but the optimal solution is wrong. The second step is to run gradient ascent on the smooth surface while simultaneously decreasing the bandwidth of the Gaussian convolution. As the bandwidth approaches zero, the smooth distribution better approximates the true distribution. Over time, we gradually decrease the learning rate to prevent the optimization from blowing up as the surface becomes less smooth. And here's an example of our algorithm using real data. I'll turn things over to Vivek now for the second half of our talk.
Thank you, John. So in the first half of this talk, we presented our new algorithmic idea for solving source separation problems. This algorithm requires a delicate balance of the annealing schedule of three hyperparameters: a learning rate eta, a noise temperature sigma, and a mixture constraint multiplier gamma. Since our initial proposal in January, we've developed a theory that justifies our approach. This theory helped us understand how to set the triple annealing schedule of the hyperparameters, resulting in a robust algorithm for source separation. Our work is under review at ICML, and a preprint is available on arXiv. The key insight here is that the squared magnitude of the gradient of p of x is on expectation 1 over sigma squared, and the squared magnitude of the gradient of p of m given x is proportional to 1 over gamma squared in expectation. This allows us to set these three hyperparameters in a principled way, greatly speeding up convergence under a few weak assumptions about the structure of the underlying distribution. Not only do we show the theory behind this method, but we also present experimental results on the image separation problem. In this first image here on the left, you can see separation results for mixtures of two CFAR10 images combined together. Our algorithm takes this mixture, the leftmost panel, and separates it out into the two component images seen in the center. The original images, sort of the ground truth that was used to create the mixture, are seen on the right-hand side for comparison purposes. Notice how our algorithm separates the mixture with very high accuracy. In the second example, we are separating a mixture composed of 4 different hand-drawn numbers. The 4 3x3 panels here on the left are summed together to create a mixture. This mixture is then fed into our algorithm, which separates it out on the right-hand side. Notice how the numbers are hardly visible at all in the middle panel, but that the algorithm does a fairly good job of separating them out. Also notice that our algorithm works on mixtures of any number of components without retraining. The only training is a generative model of the original images themselves. We never train it on mixtures of a fixed number of sources. We then scaled this up to 64 by 64 images, as seen in this example panel on a dataset called ELSIN, and we hope to make it work on full-size images in the near future. Our next step is to scale our method up to audio, where we can tackle practical problems of speech and music separation. The primary challenge here, though, is the high sampling rate of audio. Standard audio is recorded at 44,000 samples per second, whereas the ELSIN images that you see here are only about 4,000 pixels total. Just a second of audio is an order of magnitude larger than ELSIN, and ELSIN separations already take up to an hour using our algorithm. The reason our algorithm is currently slow is that we must compute batch gradients of the log likelihood with respect to the data. To make our approach more practical at scale, we are exploring stochastic variants of our algorithm called SGLD that compute gradients with respect to random subsets or patches of the data, as seen in this example image of the audio. Just like stochastic gradient descent speeds up gradient optimizations, SGLD can speed up Langevin dynamic optimizations. Furthermore, multiple stochastic updates can be computed in parallel, operating on multiple patches of data as explored in the Hog Wild paper. The goal of our work is to produce a practical, efficient algorithm that runs at scale, and we believe that we have a plan to get there. Furthermore, our approach can be modified to tackle many different kinds of constrained optimization problems. This is done by modifying the reconstruction objective and doesn't even require any new training of the model. For example, in our first paper, we already demonstrated that our algorithm can be adapted for the image colorization task. This is seen here with these example images. We also believe that we can solve other useful problems like sparse recovery of extremely compressed images or image super resolution. A different reconstruction objective would require a different annealing schedule, so we hope that our theory and our method would allow a general tool for using these generative models for conditional tasks. John and I have a unique combination of skills and experiences that make us particularly well suited to solve this problem. Firstly, we've published several papers at top conferences in the areas of audio and signal processing. Some of John's work has also been featured in venues like TechCrunch and the London Times. We've also made significant progress on this project since we first began the proposal. We've solved some of the important theoretical aspects and are quickly moving towards a full-scale solution. We're also from different labs and have different areas of expertise. John is part of the Washington AI Lab and brings a strong background in machine learning and algorithmic theory. I'm part of the Reality Lab and the Graphics and Imaging Lab, and have worked deeply on problems in the areas of signal processing and computer vision. This complementary knowledge makes us a very strong team. And finally, we'd like to thank all of you for taking the time to listen to this presentation. We know that these are uncertain and difficult times for many, and we're grateful that you're still considering applications for this fellowship. We'd also like to thank other organizations that have helped us on this journey, including funding sources up until now. This includes the UW Paul Allen School of Computer Science and Engineering, as well as the Washington AI Lab, the Reality Lab, and the NSF. Thank you.